Previously, on lists and arrays, we were trying to implement our list ADT using bare bone arrays, and everything was fine except for if we had more elements than the size of the array. We actually talked a little bit about the solution in the previous video where we wanted to extend our array. So to solve our problem, we can resize an array by creating a new array, copying the elements from the old to the new array, and then freeing the old array. Alright, so here's our solution. Let's say our array was of size 10 initially. Then I want to insert an 11th element. What I'll do, I'll just request an array of size 11 from my memory, copy the elements from the old array one by one to the new array, and then freeing the old array. Great, now our list implementation works. However, insert back will now be an O of n operation instead of O of 1 because in the worst case, you reached your maximum array length and you'll have to request a new array and copy the elements every time. There is a way to make this more efficient, and the strategy is to double the size of the array when it's full. Let's start with an array of max length 1 to make this easier to visualize. Originally, we had the implementation where we just increased the size of the array by 1 every time we reached the maximum. So it would look something like this. We insert one element, everything is fine. Then, if we want to insert another element, we have to create a new array of size 2, copy the old array, and then add our new element, and then free the old array. We want to insert another element, we do the same thing all over again. Create a new array, but this time of size 3, copy the old array, this time copying 2 elements, and then add our new element. And we'll do this every time. With the doubling strategy, this is what it'll look like. The first few times, it's very similar to the old method, but the benefits are immediately obvious when we reach 5 elements. As you can see, we extended the array to size 8, and the next 3 elements inserted will be an O of 1 operation. While the old method, it will be O of n each time. Let's actually graph this, where y is the number of times we copy an element over, and x is the number of elements inserted. For the first method, first element inserted, no copies. Second element inserted, 1 copy. Third element inserted, 2 copies. Fourth element, 3 copies. So if you look at cumulatively, you'll get for 1 element inserted, you have copied 0 times. For 2 elements inserted, you would have copied once. For 3 elements inserted, you would have copied 3 times. And then for 4 elements, you would have had a total sum of copies of 6. And then you can kind of see a pattern where once we inserted n elements, you would have copied n times n minus 1 divided by 2 times. And for the doubling method, first element inserted, no copies. For the second element, we have to extend our array, and then we have 1 copy. And then for the third element inserted, we also have to extend our array, and then we have 2 copies. And then for the fourth element, no copies this time. And then for the fifth element, we have to extend our array again, and then we have to copy the 4 elements previously. If we zoom out, we'll see that after a while, it's obvious that the first method looks more like a quadratic function, while the second method looks more like a linear function. Basically, for the doubling method, most iterations will be O of 1, unless it has to resize the array. But despite those instances of resizing the array, we can say that the amortized time for each insertion is O of 1, and it's clear by looking at the graph. We can also look at it mathematically. For the first method, this is how many copies we have to perform to insert n elements. We have 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus all the way up to n minus 1. And if you know your summation formula, you know that this is equivalent to n times n minus 1 divided by 2. So this is for inserting n elements. So to get the average or the amortized time complexity, we can divide this by n. So for each element, the average number of copies for an insert is n minus 1 divided by 2. And that is basically O of n for the time complexity. The second method, this is how many copies we have to perform to insert n elements. 0 plus 1 plus 2 and then plus 0 again because you did not need to resize the array, and then plus 4 to copy the 4 elements into your new array of size 8. And then for the 5th, 6th, 7th element, you could just insert those to the array. So it would be 0 copies for each, and then plus 8 when we resize the array, and then plus 0, plus 0. And then if you see the pattern, at the end, you would have to do n divided by 2 copies. If we remove the zeros to make it more clean, we could quickly see the pattern. 1 plus 2 plus 4 plus 8 plus 16. And then at the end, it's basically plus n divided by 8 plus n divided by 4. And then finally, n divided by 2. So if you know your summation formulas, you know that this is equivalent to n minus 1. So this is for inserting n elements. So to get the average or the amortized time complexity, we can divide this by n. So for each element, the time complexity for an insert is n minus 1 divided by n, which is basically O of 1. All right, so now you know how to create a dynamic array. We can implement the list ADT with this array, and the time complexity for the operations for our list would look like this now. So mostly nothing changed except the insert back, where now it's always O of 1 amortized. All right, that's it for the array implementation of the list ADT. Next, we will look at the linked list implementation of the list ADT. I'll see you next time.